Hello and welcome. Today we're going to have a presentation on Introduction to GIS for Policy Analysis. Let's start with the basics. So GIS stands for Geographic Information Systems. It's also, in certain circumstances, stands for Geographic Information Science. And what GIS is it's a system that focuses on spatial relationships between objects represented on data layers. And these objects can be points representing things like cities or towns, polylines, which could represent things like roads, polygons, which represent areas, buildings, political boundaries, geographic or political boundaries, and all kinds of other data. And what's very powerful about GIS is it lets us visualize, question, analyze, and interpret this data in a way that allows us to understand relationships, patterns, and trends. And you can see on the right side of your screen a kind of diagram showing a typical set of layers that you might find in a GIS file. So they can include kind of data represented in different ways, as we've discussed. Vector layers, which represent data as lines or polygons, and raster data, which is another way of representing photographs or visual information like maps. So why care as a public policy analyst? Well, one reason to care is because GIS provides a powerful visual framework for analyzing data. And another reason to care is that GIS has become ubiquitous in public policy. It's used by federal, state, and local agencies around the world for all kinds of purposes. And it's a powerful tool to gain insight into the world around us. I'd also point out that if you have a smartphone in your pocket, more likely than not, you've used GIS. And so here on the right of your screen is an image from Google Maps showing the route a pedestrian might take from the Expo station to the Saul Price School of Public Policy. And what you see here is, first of all, the environment is represented as a map with an overlay of roads and a set of points representing things like the USC bookstore or the Tudor Campus Center. And then it's got an additional layer, which is kind of interactive in this case, which is because Google Maps and other mapping programs are state of the art, showing a route between two places and showing the distance of this route. And so in this way, it's kind of got all the elements that we just discussed. A map showing topography, roads as polylines, points of interests, polygons showing buildings, and then a route showing spatial relationships between two things. In this case, the Expo station and our school. So let me jump way back to the beginning of kind of modern mapping or mapping for analysis with John Snow's 1854 cholera map. Now what this map shows is an area of London with deaths from cholera represented by these black bars that you can see coming off each street. And what I've got circled there is a pump house where water was pumped from. And what this map showed way back in 1854 was it allowed John Snow and those who analyzed it to make an association between this particular pump house and deaths from cholera. And by looking at that spatial relationship and noting that the most deaths tended to be closest to the pump house, public health officials in London made the association between cholera and water, and as a waterborne disease, and coming from this particular pump house in particular. So jumping forward about 130 years, GIS began to be used, GIS built off mapping technology, right, off paper maps. And one early application that is of particular interest to those of us in the policy analysis field is in its use in the environmental justice world. So in the 1980s and 1990s, environmental justice advocates in the US began to use GIS mapping to show relationships between low-income neighborhoods and pollution. And so it played a key role in making the case that there was something unfair going on here. So this is an early GIS map produced by the Commission for Racial Justice, which was an early group that was a progenitor of the environmental justice movement. And this shows Los Angeles. And so you may notice on the upper left corner there with the 1 in it, that is kind of like Pacific Palisades or up above Santa Monica, somewhere in there. And each kind of area, each zip code on this map has got a number, which shows the number of uncontrolled toxic waste sites in the zip code. Those numbers show the last 2 digits of each zip code. The shading shows the ethnic proportions in each zip code. And so areas with the close dots have greater than a 50% Hispanic population. And areas with the more kind of broad pattern of dots show 20 to 49% Hispanic population. And areas with the without dotting have a very less than 20%. And what you can see if you take a moment to look at this map is that many of these neighborhoods on the east side, which were predominantly Hispanic or Latino, Latinx, have a high number of toxic waste sites. You can see that there's a site kind of in the southeast quadrant there that has 11 toxic waste sites. And this map was really an early example of how GIS was used to make a policy argument and to reveal something that many people intuitively could not grasp or would not grasp, that there was an association between lower income and minority neighborhoods and a disproportionate number of toxic waste sites. The report by the Commission for Racial Justice is a really interesting read to this day, and there's a link to it there. And the Natural Resources Defense Council has a great site on environmental justice and mapping, and I've linked to it as well in the PowerPoint here. So now that I've shown you a few brief applications of GIS and kind of provided just a little bit of a glimpse of the history of mapping and how it led to GIS, I want to provide a little bit of an intro to geography. There's a few key principles in geography that are very useful when you're interpreting maps and making maps. So I'll start with Tobler's first law. And what Tobler said in 1970 is that everything is related to everything else, but near things are more related than distant things. And as an example, I've got a temperature map up here from an April day a few years ago. And you can see that there are differences in temperature as you move from left to right across the map. It's quite nice in Southern California in this map, around 71 degrees. And then as you head toward the Arizona-Nevada border there, Arizona-Nevada border, you see it's around 69 degrees, 72 degrees, very similar in temperature. It's not really till you get toward the center of more toward the center of the map, more to the four corners, that you see much of a differential between temperatures, right? There you're seeing maybe 54 degrees in, let's see, it looks like Utah or Colorado. And then as you get toward the south there in Texas, you see temperatures shoot up quite a bit. So I'll give you two quick cautions when you're using maps. One is to think about the modifiable areal unit problem. And that is basically whenever you impose a administrative border, like a state, over a map, over a geotechnical or geographic surface, you run the risk of dividing things up in a fashion that can distort things. So in this case, if you could imagine things like rivers or mountain ranges underneath the grid of states, you can see that the grid of states, if you ask, for instance, how long is the Rocky Mountains, and you're only looking at Colorado, the aerial units of Colorado could lead you astray. So it's just something to think about, and it basically boils down to how the administrative boundaries we may impose as policy analysts, political scientists, can distort the underlying geographic information, which is often quite a bit, which tends to ignore those boundaries. The other thing to remember is that your data quality is very important. If you feed garbage into a map and then you display everything in a gorgeous visualization, you're still going to have garbage in terms of what the quality of the analysis you're producing, but it's going to look good. So that's certainly a danger with mapping and really with any kind of the modern tools we use for data analysis. So just to provide a little bit more detail on those layers that I showed you before, this shows a kind of common set of layers that you might find in a GIS. Roads on the top, land use below it, other kinds of boundaries, hydrogeography or hydrography. I don't know why I can't pronounce that. Elevations, so that can be mountain ranges, and then a kind of image-based map that provides a little photorealistic picture of the world. So as you see from Goodchild here, GIS is a generic tool designed to represent a vast array of distinct types of geographic information. So you're not limited to the layers shown here. You could have administrative boundaries like we saw, states, counties, census tracts. You could have information on race, ethnicity, income levels, exposure to pollution, etc. But what we need is something to tie these layers together. And GIS provides us that essential glue that allows us to tie these different data layers together. And that is a coordinate system. So geographic coordinate systems specify locations on a spherical Earth. If you've ever heard of a latitude and a longitude, that is a system that represents a place on the globe using these, using a spherical kind of approach here, as you see. And so it's important to realize that there's a kind of distinction between the spherical coordinate system represented by latitude and longitude and a planar coordinate system that you use when you're looking at an image in 2D. So this is a key kind of somewhat technical part of GIS, but it's worth pausing on for a moment. Whenever you represent something that's spherical, like the Earth, in a flat surface, like a map, you have to project that coordinate system onto that flat 2D surface. So projected coordinate systems are models which transform the globe into a flat XY system. The key point for you as an analyst is that all PCS systems introduce distortion and thus make trade-offs. And you can see here in the image on the right, you can see kind of three common PCS, projected coordinate systems. There's planar, conical, conic, and cylindrical. So you may think, okay, cool graphics, what does it matter to me? The reason why PCS matters is because all systems distort geography in some ways. So the common Mercator projection is a map made by Europeans, early Europeans, for navigation. And thus it tends to distort countries that are far from the equator quite a bit in terms of their actual size versus how they're depicted on the map. And so if you can imagine a typical Mercator projection map of the United States and South America or Mexico, and you might think looking at that map, hey, the US is huge, Mexico's pretty small, and South America is like pretty similar in size to the United States. And that Canada is this like massive country, right? Because again, the further you get from the equator, which is the center band around the Earth, the more a Mercator projection distorts countries, makes them bigger. What you actually see when you overlay the US, Canada, and Mexico over a map of South America is you see that, wow, South America is quite a bit bigger than the United States, which I think is kind of counterintuitive. This image, this little GIF kind of makes it clearer, okay? So it's starting with a Mercator projection, and then it's resizing the countries to their true size. And as you can see, countries that are in continents that are close to the equator, like Africa and Mexico and part of South America, actually pretty much stay the same size, right? Countries that are quite a bit more northernly, like Russia or Greenland or Canada, shrink quite a bit in terms of their actual size. There's quite a bit more on the link in the previous slide that kind of explains how different coordinate systems can distort countries and distort geography, and if you're interested, it's worth checking out. So moving right along, let's look at mapping today. So maps, like everything else in our world, have gone online and they become interactive. And these online interactive maps can combine geophysical, social, economic, and political layers, just like a typical GIS, and they can also be interactive. So what you see on the right side of your screen there is a map image taken from Cal EnviroScreen 3.0. And again, I encourage you to take a few minutes, either during this presentation or after this presentation, to check out and play with Cal EnviroScreen. And what this system allows you to do is it allows you to see the pollution burden of every census tract in California. And it not only provides a kind of geophysical information about the land mass, right? You can see there's a kind of base map under there, somewhat visible, showing topography and elevations. You can see there's some points representing cities, and then you can see the census tracts overlaid. But what's interesting is those census tracts don't just show kind of physical information on pollution, right? Particulates per square mile or something like that. Those boundaries, those polygons, also contain information on the social and ethnic and economic makeup of each census tract. So what this map is doing is it's uniting both geophysical information, geotechnical information about pollution, social information about where ethnic groups live, economic information, and then political layers. So it's got the whole kit and caboodle. I'll end and wrap up here by providing a few kind of hints about future directions or suggestions or ideas about future directions. So one very cool trend is the creation of story maps. Story maps combine the maps we've been looking at with text, audio, and video in a way that allows you to tell a story. And Esri, which is one of the large makers of GIS software, has a free online system where you can make story maps. So I encourage you, perhaps for your projects here in PPD 554, to experiment with story maps and see how they can help enliven your presentation and help you make associations and see patterns that you might not see otherwise. Looking toward more sophisticated methods that we're not going to get into in this discussion is combination of GIS with statistics. And that leads to a whole field called spatial statistics. And in fact, you can even go further than that. You can combine GIS with statistics and with agent-based modeling to actually simulate social systems. So on the right side of your screen here is an image grab from an early version of the Sustainable Energy Modeling program that I helped create at Claremont Graduate University when I was working on my PhD. And I've got a link there to the chapter that we discussed this particular model in, called Rethinking Environmental Justice in Sustainable Cities. And the reason I bring this up is because it represents community-based organizations as those little smiley faces over a GIS grid. And this is actually showing the kind of Inland Empire region around Chino Hills is in the base of the map there. And the black line is a power line. So what we were doing with this map was studying how the proposed route for the Tehachapi Renewable Transmission Project might cause social disruption and what the possible reactions of different groups might be in the path of the line. And so for this project, we combined census data, GIS data, route data of the power line, And then we actually did modeling using an agent-based system to figure out what kind of interactions might happen and what the eventual behaviors and sentiments of the groups in near the line might be. So I hope you've enjoyed this presentation. I think you'll see that GIS is an incredibly deep field. It's really, there's many, many fields within it. Spatial statistics being one, visualization and cartography being another, spatial analysis being a kind of another branch of it. There's a lot to it, far more than we can cover in this introductory talk, but please check out the links in the attached deck and experiment with some of the sites that are available online and see if there's anything that you find interesting. There's lots of other classes you can take at GIS, on GIS here at USC. And again, it's a rich field with many potential applications for public policy analysis. Thanks for your time. And if you have questions, please reach out. I look forward to speaking with you soon.